In this video, you and I are going to take a look at adding multi-protocol BGP to our PE routers, which are in our topology R1 and R5. Let's begin. Here are the opt-out questions for this video. So take a moment, pause the screen if you'd like, and if you know the answers to these questions and you understand the concepts regarding these questions, hey, I'll see you in the next video. For everybody else, let's dig in. Our objective for you and I in this video is simple. We want to implement this portion right here, the border gateway protocol between our PEs from R1 over to R5. And this is going to be an internal BGP neighborship. They're both in the same autonomous system. And when we set up BGP initially, we'll create the process, we'll identify the BGP peers. We're going to want to point to each other as far as peers go to their loopback. So R5 will be 5.5.5.5. and R1 will be 1.1.1.1. We'll also want to source those BGP sessions from those loopbacks. So that way, anytime R5 receives a BGP route from R1, it'll see the next hop as R1's loopback. And vice versa. If R5 advertises a route over to R1 through BGP, R1 can see the next hop as 5555. Now, once we enable border gateway protocol between two peers, by default, IP version 4 is supported. It's assuming, hey, you want to exchange IPv4 routes. Now in our situation, we really don't care too much about IPv4 route exchanges through border gateway protocol. What we want to do is we want to exchange the VPN v4 routes. That's those routes that we've learned from a customer that we've taken out of the VRF and put into BGP with the additional information such as the VPN label and some additional tagging information to associate that route with Acme Site 1. So to do that, the next thing we're going to do is we're going to activate VPN v4 capability between R1 and R5. And now when we do that, those BGP neighbors are going to be supporting VPN v4. That's those VPN routes that have that VPN label on them, as well as native IPv4 if we want to use that. And that, my friends, is what makes multi-protocol BGP. We have the capabilities of carrying multiple types of routing information. In this case, we could carry IPv4 as well as VPN v4 routes and exchange those between two BGP neighbors. And if we wanted to, we could actually turn off the feature of supporting IPv4 if you know you're never going to use it, but we would still call it multi-protocol BGP because it's carrying something above and beyond IPv4. In our case, it's carrying VPN v4. So it's really interesting. To enable VPN v4 capability, we're going to enter a separate configuration mode within the BGP process. So it's like this. We walk into BGP configuration mode by typing in router BGP in our autonomous system number, and then we're going to enter a separate subcompartment, and it's called an address family for VPN v4. And once we press enter, we're then in that separate configuration mode just for VPN v4 functionality. And then, when you and I are sitting in this configuration area within BGP, we'll simply activate each neighbor. So from R1, we'd say activate R5, and when we're in R5, we'll say activate R1. Now, I mentioned that these VPN v4 routes have additional baggage, additional tagging information. They've got the VPN label that's attached to these routes. They're also going to have something called a route target. And these route targets that you and I will be configuring in a separate video when we cover VRFs, these route targets are used to identify exactly who the routes should be shared with. Now, these route targets that are also part of these VPN v4 routes, they're attached as something called an extended community. And the extended community is just a value, some number. So inside of BGP, if we enable extended communities, we can attach that type of information to a route and forward that information along with the route. And although we will have a separate discussion and video on route targets, I'll tell you right now that the purpose of a route target is to control where VPN v4 routes are advertised. For example, this network that's coming from Acme Site 1, 172.16.00/12, as that network is advertised and R1 learns it, and it's going to learn it on the VRF for Acme, when that route gets exported out of the VRF and into multi-protocol BGP as a VPN v4 route, we're going to tag on a route target. And let's say the number that we use, just as an example, is 9:9. And it's just a value. And this is sent as an extended community associated with that VPN v4 route. So what does 9:9 mean? Well, if we've configured over here on R5 that R5 should pay attention to the route target of 9:9. And anytime it sees that route target, to go ahead and take it out of BGP and import it into the VRF for Acme so it can advertise it up to Acme Site 2. So the way that you and I are going to use a route target is we're going to use it to control where specific VPN v4 routes are advertised. Should Acme Site 2 be aware of this information over from Site 1? And the answer is it depends on how we configured R5 and the VRF for Acme Site 2 regarding importing VPN routes based on route targets. So as I mentioned, we'll take a closer look at implementing that. But for right now, as part of BGP, we also need to tell inside of the address family for VPN v4 that we need the peers to support and be able to forward back and forth these extended communities, because the route targets are sent as extended communities. So if the routers don't support extended communities or aren't willing to exchange extended community information, effectively it means they won't be willing to send route target information, which is going to break our MPLS Layer 3 VPNs, because then if we don't have any route targets, our routers won't know which of all those VPN v4 routes in BGP should be taken out and imported into the VRF so they can be advertised to a specific site. So long story short, we need to support extended communities to support route targets. So here's what you and I get to do. We're going to walk through step by step implementing Border Gateway Protocol between R1 and R5. And before we start the implementation of this new BGP feature, we want to make sure that the existing network is working, including the entire path between R1 and R5. And we'll also do some commands to verify that our LSP is still functioning. And the reason I emphasize that is because as you lab this up along with me and practice these commands, I want to make sure you're set up for success. And having a great infrastructure first that's working is a key to that success. The first thing that we got to do is verify that we have a path, a working path from R1 to R5. We're going to ping the loopback of R5 and source it from R1's loopback. That way we can verify we have reachability in both directions. If we wanted to view the MPLS forwarding information right here in R1, we could do a show MPLS forwarding table for that same network of 5555. And here it's saying, yep, if I was going to forward to 5555, I would impose label 205, send it out gig 1/0, and then R2 would take that label 205 and swap it out for whatever label R3 locally had for that network. And that would be our LSP, our label switching path. If we use the command show IPseth for that same network, it would also reconfirm that that label of 205 is the one that R1 would impose on it, as it forwarded a packet that was destined for 5555, and again 205 would be the label R1 would impose on that as it sent it on to R2. And if we wanted to see all the labels in the label switching path for network 5555, we could just do a trace route to that destination. So R2 is using label 205, R3 is 305, and R4 is 405, and that's because I just rebooted these and they all came up in a very similar manner. We can mix this up just a little bit. Let's go to R3, and then configuration mode. Let's do a no MPLS IP, and then bring it back up with MPLS IP. I'm going to do that a couple more times with a no and a yes, and that'll mix up our labels quite considerably. If we go back to R1 and do that same trace to 5555, we see that now that R3 is currently using 315. Again, it just randomly grabbed that as an available label, and it associated that label with 5555, and then it advertised it via LDP to its neighbors R2 and R4. So next, let's go into configuration mode, and let's create the BGP process. Let's create router BGP 65536, and let's identify neighbor 555 as being our peer in that same autonomous system, which makes R5 an internal BGP neighbor. And secondly, let's specify the update source as our own loopback 0. That way, if we send any routes via BGP over to R5, it'll show a next hop as 1.1.1.1. Now, by default, BGP is expecting to form a neighborship to advertise and receive IP version 4 routes. If we want to crank it up a little bit and tell this router that we also want to support VPN v4 routes in addition to IPv4 routes, we need to enter that special VPN v4 configuration mode, which is called an address family. So we'll type in address-family space VPN v4. That takes us into this new section, and then we'll simply activate neighbor 5555 for VPN v4 route support. And secondly, we'll also make sure that we're able to send extended community information between R1 and R5. Now, as long as R5 agrees with all that and is also similarly configured, R1 and R5, once we configure R5, will be able to exchange and send back and forth VPN v4 routes and as well as the associated route targets that we associate with any VPN routes. So if you're labbing this up alongside of me, which I hope that you are, go ahead and pause me right now and configure R1 with what you've seen me do. And then when you're done, go ahead and restart me and we'll configure R5 together. So we'll make a road trip over to R5. And on R5, we'll go into configuration mode and we'll create that same autonomous system number for BGP of 65,536. And we'll say that our good buddy is neighbor 1111. And the remote AS for that neighbor is 65,536, same as ours. So we'll be iBGP neighbors. And the update source we're going to specify as loopback 0. So that way, anytime we advertise routes over to R1, the next hop will be shown as 5.5.5.5. Now we have a neighborship that came up, and this neighborship is supporting IPv4 because that's what BGP expects by default, because we haven't yet set up R5 to support VPN v4 routes. That's why we're getting that notification about that capability. Now, notifications in BGP are always bad news. Something went poorly. So even though we do still have a neighborship for IPv4, R5 is saying, hey, R1 is trying to negotiate VPN v4 support. I don't have that set up, and so I can't support it. However, you and I can fix that by simply going into the address family for VPN v4 here on R5 and say, yep, I do want to activate this capability with neighbor 1.1.1.1, and I do want to go ahead and be able to send extended community values to that neighbor. And once we do, we should also have support for VPN v4 routes between R1 and R5. And look at that. That looks awesome. So we got our neighbor up initially for IPv4. And now we have a session that's supporting VPN v4. So how would we go about actually verifying that those capabilities exist? We could do a show IP BGP neighbors, and that gives us like 6 pages of output. Or we could granularly section that off and say show IP BGP neighbors pipe section capabilities, and it'll just show us that portion of the output from show IP BGP neighbors. So regarding neighbor capabilities, it's saying it's supporting address family IPv4 as well as VPN v4. Now in BGP, unlike other routing protocols like IGPs, BGP uses TCP port 179 to initiate the communication channel between one BGP speaker and the other. And the device that initiates the session is going to use some source high random port number going to TCP 179 at the other side. So if we want to see the details of, okay, which port was used on a device for a certain service, we can do a show control plane host open ports. And this has a lot of great information. So we're listening on port 23 for telnet. This one right here is our LDP session at port 646. So because R5 had the higher LDP router ID, it initiated the connection to R4 for LDP. Then we have, and I'll put this in green, here's our BGP session right here. So it appears that R5 initiated this session. So it used the high source port of 27,003. It was just an unused available TCP port. It connected out to 1.1.1.1 at the BGP well-known port of 179. They negotiated with each other, set up their session, and now we have an iBGP neighborship between the two of them. It also appears, based on this entry right here, that the host at 1.1.1.1 also initiated a session. And it, for this session, simply selected a high port that wasn't in use and connected over. And then we also have this guy simply listening on port 179 for any incoming BGP requests that might be coming in. And we're also listening on this UDP port right here, which is LSPV echo. There is such a thing as an MPLS ping, and this service, because it's running, has the ability to help contribute to the response of that ping. For example, if we did a ping MPLS IPv4, the IP address of R1, and we set the EXP bits to 5, repeat count of 2, verbose. And we can use a command like this when we start troubleshooting our LSPs. Let's say we have multiple LSPs, and we have a certain LSP that we want to use when any traffic is marked, for example, with an IP precedence of 5. And if something goes wrong, we can go ahead and use these codes to help debug and interpret what the problem is or where the problem is in the LSP. So if we take a look at those open ports one more time, I'm thinking that if we did a clear IP BGP like that, that's going to break any type of BGP neighborships and reestablish those neighborships. And then if we use the up arrow key to show the open ports again, this is traditionally what we would see. We're going to have one session. In this case, it was R5 who initiated the connection to port 179 on 1.1.1.1. And they're using that single session to support the capabilities of IPv4 and VPN v4. It's just that initially, when I brought up just the IPv4 support, it established a session based on that. And then when I added the VPN v4, it said, oh, we want to add this as a feature. I don't want to mess anything that's currently going up with IPv4. So let's go ahead and create a second session. So if we do a show command again, just to verify our capabilities, we should still have IPv4 and VPN v4 capabilities with our neighbor R1. And sure enough, there we do. And the reason I mentioned the multiple possible sessions to you is because if you're labbing this up and you're putting in one command, then the next, it's very likely that the first time you do it, you may have two sessions. But then after you save your configs and then reboot, it's very likely, like here, that you're just going to have one BGP session between the two peers supporting the capabilities of IPv4 and VPN v4. So if we just want to issue the command show IP BGP neighbors, that would give us all the output and we can simply scroll through it. Here's our neighbor capabilities right here. Here's our network activity regarding advertisements in IPv4. You'll notice we aren't currently advertising any IPv4 routes, so that's empty at the moment. And if we scroll down a little bit more, here we have the VPN v4 routes. Also, none sent and received because we don't have any VPN v4 routes yet inside of multi-protocol BGP. So what I'd like you to do is save your configuration. So on R5, we're going to do a copy run start or WR. Whichever way you want to save your configuration is fine, as long as it shows up in startup config. And over in R1, we want to do the same thing. We'll do a WR, copy, run start, effectively the same thing. So now, in the ingredients list, we now have multi-protocol BGP running between R1 and R5, which is a critical ingredient to have. What I would also ask you to do right now, besides saving your config, is I'd also like you to add another Ethernet module to R1. So I'd like you to put it in slot 2, and I'd like you to also add that Ethernet module to R5. And that'll support the two fast Ethernet interfaces that are going to go off to our customer sites. In fact, while you're at it, I'd also like you to add to your topology these routers. Acme Site 1, CBT Site 1. Acme Site 2, CBT Site 2. And if you would, use that same Ethernet module in these routers, and that way we can use FA2/0 here, and FA2/0 here, and FA2/1 here, and FA2/1 here. And we'll have the same hardware configuration over at R5. And by adding those interfaces and adding these four routers, we'll be prepared for our next step, which is adding VRFs to R1 and R5, and including the appropriate interfaces as part of those VRFs. So let me bring over what GNS3 will look like once you add those devices. So I've got Acme 1 and CBT 1, Acme 2 and CBT 2. And if we open up any one of these, we'll just double click on it, select the name of the router, go over to slots. In slot number 2, we're going to put this module, PA2FE-TX. That's a 2-port fast Ethernet module. And we'll put it in slot 2, and we'll do that for each of these routers that are circled in pink. And then we'll use the connector tool to make the connections from CBT1 2/1 over to R1 2/1. From Acme 1 FA2/0 to R1 FA2/0. And similar treatment over on the right hand side as well. So what I'd like you to do right now is implement the BGP, add the additional routers, add those modules, save the configs both in the interface at the CLI of the routers and through GNS3 so it's ready for you the next time you bring up this topology. I have had a great time, and I'm glad that you joined me for this video. Please take a moment, review the opt-out questions, and make sure that you add that BGP, add those router modules, and those 4 additional routers to your topology, and save everything. And that way you can be squared away and set up for our next video as we add VRFs. Again, thanks for joining me. I hope this has been informative for you, and I'd like to thank you for viewing.